A single missing API endpoint, a flaw in the system architecture, could render a perfectly trained machine learning model completely useless? That you could have an algorithm capable of saving millions, but no way to plug it in. This is the story of how we move beyond simple, hard-coded rules to build a sophisticated fraud detection model. We'll go deep into the feature engineering, the specific machine learning techniques used, and the metrics that proved it worked. But more importantly, I'll show you the catastrophic, near-fatal deployment error we made and how a temporary, low-tech workaround ended up saving the project. Our company manages corporate benefit cards, a system where employers fund cards for their employees to use. This simple model, however, was a prime target for increasingly sophisticated fraud, from card cloning and mail interception to fraudulent merchant setups. To combat this, we relied on a commercial risk management platform. The fraud prevention team's job was to act as system administrators, manually programming in a series of IFN ELZ statements for corner cases. The logic was purely empirical. For example, if the same card is used more than 5 times in a period of just 10 minutes, the system should block that card. Another rule was the impossible travel rule. If a purchase is made more than 800 kilometers away from the previous purchase and less than an hour has passed between the two, the system should also block the card. This static rules-based approach had critical vulnerabilities that fraudsters were actively exploiting. Lack of adaptability. The rules were static. They couldn't learn. As fraudsters evolved their tactics, using smaller transaction amounts or spreading activity over slightly longer periods, our rules became obsolete. We were always reacting, never anticipating. High-dimensional blindness. The engine could only handle simple, low-dimensional relationships. It couldn't spot complex patterns across dozens of variables simultaneously. A fraudulent transaction often looks normal if you only check one or two things, but its fraudulent nature becomes obvious when you analyze 50 variables at once. The data gap. We estimated that our rules-based system was failing to detect around 30% of confirmed fraud cases. These were only discovered weeks later when a customer would call to dispute a charge, by which point the funds were irrevocably lost. The financial drain and the poor customer experience were unsustainable. We knew the answer was in the data. The goal was to build a predictive model, but a model is only as good as the features it's trained on. We moved beyond the raw data and started engineering new, more powerful variables. Our data sources included raw transaction logs, timestamps, amounts, merchant IDs, locations, merchant category codes, MCC, and historical data. Customer chargeback history, our labeled fraud data. Historical customer spending behavior. From this, we engineered a new feature set. Here are a few examples. Transaction amount versus the user's average. We would ask the system, is the amount of this purchase significantly higher than what this customer typically spends? Time since the last transaction. Was the last purchase made just seconds ago or days ago? A very short interval between purchases could be a strong red flag. Is it an unusual store category? For example, is this customer, who normally only buys groceries, suddenly spending money at a high-end electronics store? Distance from the last location. The model would calculate the exact physical distance between the location of the previous purchase and the current one. Is it a night transaction for a daytime user? Was this purchase made in the middle of the night, when that specific customer usually only uses their card during business hours? These features gave the model the rich contextual information the old rule engine never had. We needed a model that was both highly accurate and interpretable. The fraud team needed to understand why the model flagged a transaction, not just that it did. A black box neural network was too opaque for our needs. We chose a gradient boosting machine, GBM, specifically using the LightGBM library for its speed and efficiency. Here's a slightly more technical breakdown of why. Ensemble method. Gradient boosting isn't a single model, it's an ensemble of many weak learners, typically decision trees. Sequential learning. It builds these trees one after the other. Each new tree is trained to correct the errors made by the previous ensemble of trees. This sequential process allows it to focus on the hardest to classify cases, making it incredibly powerful. Interpretability: unlike some other complex models, we could use tools like Shapley additive explanations, to see exactly which features contributed most to any single prediction. If the model flagged the transaction, we could tell the fraud team it was because of an unusual location combined with a high transaction amount relative to the user's average. We trained the model on a labeled dataset of millions of historical transactions, carefully splitting our data into training, validation, and testing sets to prevent overfitting and to get an honest assessment of its performance. The output wasn't a simple fraud not fraud binary, but a probabilistic risk score from zero point 0.0 to 1.0. When we evaluated the model on the holdout test set, the results confirmed our hypothesis. Recall improvement: the model detected 18% more fraud than the rule engine. In data science terms, this means we increased our recall, the percentage of total actual fraud cases that we successfully caught. Precision improvement: the false positive rate dropped by 15%. This means we increased our precision. When the model flagged a transaction as fraudulent, it was much more likely to be correct, reducing the number of legitimate customers impacted by mistaken blocks. Finding the unseen: most impressively, 80% of the fraud cases identified by the model were unique to it. These were the complex, multivariable fraud patterns that our old static rules were completely blind to. We had achieved the data scientist's dream, building a model that was both more sensitive and more precise. We had our pickle file, our metrics were stellar, and we were ready for deployment. We walked into the final implementation meeting with IT and engineering, ready for our victory lap. We presented the results and said, "Okay, let's get this into production. We need to call the model's predict proba function for each transaction in real time." The room went quiet. The lead architect explained the reality of our infrastructure. The core transaction processing system was a legacy monolith. There were no microservices, no REST API endpoints for real-time model inference. The only way data left the monolith was through a nightly ETL extract transform load job that pushed the day's transactions into a data warehouse for reporting. Our model needed to make a decision in under 50 milliseconds. The architecture could only give us data that was 24 hours old. We had designed a state-of-the-art AI detective, but the police station had no phone lines to receive its calls. The project was dead on arrival because we, the data team, had never consulted with the people who build and maintain the systems. After the initial shock, we pivoted. If real-time was impossible, what could we do with the 24-hour delay? We devised the workaround. We set up a daily cron job on a server. Each morning, a Python script would trigger, pulling the previous day's complete transaction log from the data warehouse. The script loaded our trained gradient boosting model from its pickle file and ran all 24 hours of transactions through it. It would then generate a simple CSV file containing only the transactions that the model assigned a risk score above a 0.25 threshold. This most wanted list was automatically emailed to the fraud investigation team. It was a manual, reactive process, but it was infinitely better than what we had. It allowed the team to investigate the highest risk cases from the previous day, and it paid off almost immediately. Within the first week, the list flagged a bizarre pattern of high-value sales at a newly accredited merchant. The team investigated and confirmed it was a fraudulent setup designed to cash out stolen card numbers. Because they caught it less than 24 hours after the transactions occurred, they were able to contact the payment processor and cancel the settlement transfer, preventing a $50,000 loss. That single win proved the model's ROI and secured the funding to overhaul the architecture for real-time inference. But the lesson was clear. A machine learning model is not just a Python script. A great algorithm without a production-ready deployment path is just an academic exercise. The biggest mistake was not a flaw in our math or our code, but a flaw in our process. We failed to consider machine learning operations and system design from day one. If I could go back, the first meeting would not be about data. It would be a whiteboard session with an architect mapping the data flow from the point of transaction to a potential model endpoint and back. We learned to start with the deployment target and work backward. Thinking about the model is easy. Thinking about the system is what turns a theory into a solution. Thank you for watching. If you enjoyed this video and want to see more content like this, don't forget to subscribe.